This is lesson 6. It's the final lesson in unit 6 for natural logarithms today. We say a natural log function is log base e of x, and we can rewrite log base e of x as ln x, or natural log of x. The natural log of x is the inverse of the function y equals e to the x. In this first screen, we see the properties of logarithms. And anytime we have positive numbers m, n, and b is not equal to 1, then the following properties apply. I'm going to use capital M and n. So the product property says if you have the natural log of one number, we'll say m, and we're adding the natural log of another number, and we'll say n. When you have the sum of two logs, you can rewrite that as the product of m times n, and that's the natural log of the product is the sum of the two logs. Likewise, the quotient property says when you subtract the natural log of m minus the natural log of n, you can combine those to be a single natural log by taking the quotient m divided by n. The natural log of m divided by n is the difference between the two logs. The power property says when I have a natural log of a number raised to a power, we can multiply that power times the natural log of that number. And then finally, the change of base says that if you have a natural log of some number, and again I'm saying m, that I can use the log of any base for that number and divide it by the log of any base times log base c of that base, which this base would be e in this case, as long as the denominator is not 0. So let's look at the graph of y equals e to the x and see how it is the inverse of the natural log, how they're inverse functions of each other. So if we use the table y equals e to the x, y equals e to the x, when x is 0, e to the x is 1, and using my calculator, when x is 1, e to the 1 is about 2 7/10, and when x is 2, e is about 7.4. So graphing that over here on our graph, 0, 1, and 1, 2.7, and then 2 is 7.4, so it's up here somewhere. We have that exponential growth, y equals e to the x, looking something like that. And inverse functions, when you interchange an inverse, we're going to use this table to represent y equals the natural log of x. So the x becomes y and the y becomes x in our table. 2.7 is 1 and 7.4 is going to map to 2. So our logarithm graph would be 1, 0, 2.71, and then 7.42, and that graph would appear like our logarithm graph. This is the natural log of x. Then algebraically, if we consider log base, or y equals e to the x, if we change the x to the y to x and the x to y, and we rewrite this, we would say the natural log, or log base e of x, is equal to our y. This is my inverse property. So y equals e to the x is the inverse of the natural log of x. In example 2, we're going to simplify the expressions. So remember that this natural log base e of 1 is equal to the power if e to the power is equal 1. So when you think that through, we need e to be to the 0 power to give us 1. So the natural log of 1 is going to be 0. And if you want to create that, natural log of e to the 8th is like 8 times natural log of e. Well, we know the natural log of e is just 1, since e to the 1 is equal to our number e here. So natural log of e is 1, and 8 times 1 is simply 8. And again here, natural log of e is 1 by definition. And in example D, we have 1/6. This is like 1/6, or 3 times the natural log of e divided by 6. So 3 over 6 is 1/2. And 1/2 times natural log of e, well, we just saw in part C that the natural log of e is 1. So 1/2 times 1 gives us 1/2. So we have an answer of 0 and 8 and 1. And finally on part D, 1/2. In example 3, we want to be able to rewrite each expression as a single logarithm. So in this second part, I want to put that power 2 back into the power on the 5. So that would become 5 to the second power, or 25. And when I have the sum of two logs, I can rewrite that as the product of a single log, where 25 times 7 is 175. So the natural log of 175 is a simpler way to rewrite natural log of 7 plus 2 times the natural log of 5. On part B, again, I'm moving that power 3 back onto the x, and the 2, I'm going to move that back onto that expression, 2x to the second, which is going to create 4x squared here, but it's a subtraction problem, so we can rewrite the natural log as a quotient of x cubed divided by 4x squared. Now, if you want to go one step more, we can simplify by dividing x squared into the x cubed, which would finalize our answer to be natural log of x divided by 4 as a single logarithm, natural log of x divided by 4. In part C, the 1/3 in the front is going to be a cube root. So we want to put that back as the natural log of x divided or multiplied by 8 inside the parentheses, and raise that to the 1/3 power. And then put the 4 back on the y to the 4th. And the difference of two logs is the quotient of a single log. But the natural log of the cube root of 8x divided by y to the 4th, we can simplify that cube root of 8 and bring that outside of the radical. So natural log of 2 cube roots of x divided by y to the 4th is the single logarithm for that expression. And finally, we could say 3 times natural log of e. That's just 3 times 1. But then I couldn't write the expression as a single logarithm. So I'm going to just leave that as natural log of e cubed plus natural log of x squared plus natural log of y. That way, we're going to have just one single term, one single expression when we get to the end. Otherwise, I would have 2 terms by having 3 plus the natural log. So we're going to make it the sum of 3 logs can be the product of e cubed, x squared, and y. This way I'm following the directions, writing the expression as a single logarithm instead of writing it as 3 plus the natural log of x squared y, since that's not a single logarithm. So it's just a preference that whatever your teacher prefers. In example 4, we're going to solve equations here. We've got 3 easy ones. I want to remind you of the definition of logarithm. If I have the natural log of x is equal to a power, I know that that can be rewritten as e to the power is equal to that number x. For example, in part A, we could think of this as e to the second equals x, and then using our calculator, this is the exact answer, this first step, and using our calculator, e to the second is about 7.389. So whether you want the exact answer here, x is e squared, or the decimal approximation. In part B, we want to use the properties and multiply 2 times the natural log of 3x plus 5, and that's equal to 4. And then we could divide both sides by 2 to get natural log of 3x plus 5 is 4 divided by 2, so that's equal to 2. And then use our definition here. If you have the natural log of a number equals to a power, then e to the power, so e to the second, is going to be equal to the number 3x plus 5. Then solving for x, we want to subtract 5 and divide by 3. There's our exact answer. Divide by 3. I wrote a 2. So let's fix that. Divide by 3. And if you want to have the approximate answer, we need our calculator. And my calculator tells me that an approximate answer is 0.7964. So we have the exact answer and the approximate answer. And then the last part C, we're looking at natural log of 2x plus natural log of 3, and that's equal to 2. So we want to combine the natural log, the sum of the natural logs to be 2x times 3. So that's going to give us 6x, and that product, natural log of 6x, is equal to 2 when e to the 2 is equal to 6x. So to get the exact answer, x is e squared divided by 6. That's the exact solution. And then to get an approximate solution, I'm going to check with our calculator. The value for e squared divided by 6 is about 1.2315. So depending on what you need, either exact or approximate, based on the situation at hand. In example 5, we want to solve and check exponential equations, where example 4 was natural log equations. These are exponential equations. So we're solving for x in this case. And 2e to the negative x is 25 minus 3, so that's 22. And dividing by 2, e to the negative x would be 11. And we can get the natural log of both sides, so that negative x is times natural log of e is equal to natural log of 11. So here I'm doing two things at one time. I took the natural log and then moved the power negative x. But natural log of e is just 1. So we have negative x is equal to natural log of 11. So x is equal to negative natural log 11. That's our exact answer. And if you need the approximate answer with your calculator, negative 2 and 39 or 40 hundredths is an approximate solution. And again, you can take this number and go back to the original and check in that original that that solution works. Here, again, taking natural log of both sides, e to the x minus 2 power is equal to natural log of 12. So we know natural log of e is 1, and the power comes down, x minus 2 times 1, this is 1, is equal to natural log of 12. So solving for x is 2 plus the natural log of 12. This is my exact solution. And an approximate answer to check into the equation to make sure that this is valid is 4.4849. Here's my approximate solution. And then lastly, in example 5, part C, we have 15 and we're subtracting 5, so 15 minus 5 is 10. Taking the natural log of the left and the natural log of the right gives us the ability to move that power, 3x, down into the front as a multiple. And we got 3x times natural log, which is 1. So 3x is equal to natural log of 10 when x is natural log of 10 divided by 3. And again, this is my exact answer. And if I want an approximate answer to check my work, that would be about 0.7675 as an approximation. And again, I'm leaving the checking in the equation for you to do. And then our very last example is a real-world example and application, and we're using the formula here. H is 1 over r times natural log of p divided or minus natural log of a, and that models the time that it takes for bacteria in a culture to decay. So this is a decay formula. H represents the number of hours, r is the rate of the decay, p is the initial bacteria population, and A is the reduced bacteria population. So for part A, we have a scientist determines that some antibiotic decays a population of 18,000 bacteria to 4,200 in 24 hours. So following the definitions here, it looks like the P is 18,000, that's our initial. And the A, that's the reduced bacteria, that would be 4,200. And it seems like the hours is 24. So we want to find the rate. We don't know the rate. That's what we're looking for, the rate of decay. So setting that up in the formula, 24 is 1 over the rate times the natural log of 18,000 minus the natural log of 4,200. So we could take that 18,000 divided by 4,200 and find out with our calculator. Let's see, let's multiply through by r, and we want on our calculator to calculate 18,000 over 4,200. So we can get rid of a few of those zeros. So we're looking for natural log of 180 over 42. And then dividing that by 24, so r is 2r, 24r, is 1.455287, and dividing by 24, we've got about 0.606. So this is our rate, and to write that as a percentage, we'd multiply by 100. So that moves a decimal. And then we know that the rate of decay caused by that antibiotic is about 6.06%. So we've calculated that rate of decay that the antibiotic caused. And then in part B, it tells us a laboratory assistant test an antibiotic that causes a rate of decline of 0.16. How long should it take for a population of 5,000 bacteria to shrink down to 400? And we can use that same formula. So we want to solve for hours. What's the hours of 1 divided by the rate, 0.16? And we've got natural log of the population, that's 5,000, minus the natural log of the reduced population, that's 400. So we're looking at 1 divided by 0.16 and doing natural log of 5,000 divided by 400. So natural log 5,000 divided by 400 would be 4 over 50, which is about 2.52573, and we're going to divide that by 1600ths to get the hours. So that's about 15.786 hours. Now, if you convert 0.786 of an hour, we would find out that 0.786 of an hour, that there are 1 hour has 60 minutes. So this is about 48 minutes. Therefore, we can say that the population will shrink to 400 bacteria, after 15 hours, because we got this up here, 15 hours and 48 minutes. And that, my friends, finishes up Chapter 7, Exponential and Logarithmic Functions.